Hi, my name is James Falconer with FluidTech. It's my pleasure to introduce Dries Van Loon. Dries is Vice President of Customer Success at Nanoprecise, and he'll be demonstrating for us reliability versus net zero, linking fault modes to carbon footprints. I'll let him take it away. Thanks.
Hello, everybody. Can you hear me okay, Frank? I assume that's a yes. So welcome, everybody, and excited here to be part of this LRVS conference, right? I think it's been a great addition to the conference landscape and something focused on lubrication, and then combined with the bigger topic of reliability is really great to see out there, right? Because there's not so much really focused on this lubrication part of it, but it's a very important factor. And one of the other things that I think is very exciting here is that we see now this net zero, or I'm not sure how they called it, but a track specifically focused on kind of these topics that are around net zero and greenhouse gas emission, and it kind of shows that this is an active topic, right, in most companies. So I'm very excited to that in our company it has been a very active topic and discussion for the last 12, 24 months, and that we're actually able to bring some solutions here that we're implementing today at scale. So happy to kind of talk you through today the reliability versus the net zero, and how the traditional fault modes that one predicts with or defines during their reliability effort can also be linked to energy consumption, and basically use them in their net zero pursuit, right? So we'll talk about net zero and greenhouse gas emission, right? What does that all mean, and how does the industries that all of you and myself as well typically serve, right, with rotating equipment, how do we contribute to this? So what can actually be our influence, right, if we're doing these types of improvements? Very briefly, predictive maintenance. Today, where are we, and how is it being used, and then making that link to the equipment efficiency, right? And that's really the key driver here if we're trying to improve our greenhouse gas emissions, then basically our efficiency has to improve, right? Obviously, we cannot just shut everything down or replace everything with more energy efficient equipment, but we can put in an effort to try to run whatever we have as efficient as possible. And that's really where and being able to measure that and then monitor that over time is really adding value, right? So that's where we come to the fault modes versus energy consumption, and how those two can together basically add more value. And then we'll go over a couple of key takeaways, and I'll take any questions. I think if you ask questions in the chat, they'll show up here on the screen. So if it's on topic, I'll try to answer them as we go. Other ones I'll leave till the end and try to answer everything. If we don't get to it today because half hour goes fast, then potentially I'll follow up by email to make sure you get your question answered. Okay, so looking at net zero and greenhouse gas emissions, right? And basically, net zero is a very active topic in every boardroom, in every company. All the big Fortune 1000 companies have made some expression of like, hey, how they're gonna attack net zero, or how are they planning to reach net zero with their company, right? But kind of looking at it as from afar, right? Looking at global greenhouse gas emissions, as you can see on the right-hand side there, 70% is coming from energy production, right? And what does that really mean? That out of that 73%, basically 25% of the total greenhouse gas emissions today are from energy generated that are used in industry, right? So in manufacturing, in other types of industries. So we kind of leave the actual power generation industry itself out of it, but we're looking at the consumer side, right? So 25% of all greenhouse gas emissions are basically produced to generate energy for manufacturing, for mining, for all those kind of consumers of electricity. And then if we look at that and zoom in on a couple other studies, it basically comes that roughly 50% of all industry, right? Obviously, it depends on which specific industry you're looking at. But in general, it said that 50% of all industrial energy usage is being used by rotating equipment today, right? And obviously, somebody as myself, as a Cat4 vibration analyst, I kind of live and breathe in the rotating equipment world, and a lot of you, I think, do the same, right? Because it's typically at the core application for obviously lubrication, but general reliability efforts, right? So basically 50% of that energy goes to there. So simple sum there, right? It comes to that basically 12% of, minimum 12% of worldwide greenhouse gas emission is being generated because of industrial rotating equipment, right? So if we add, so that's the part where we can contribute, right? How can we now reduce the greenhouse gas emission of that rotating equipment? And that's really what drives myself, other team members at our company to improve there, right? Because that's where we can make an active contribution. And if we, for example, can improve rotating equipment energy, rotating equipment efficiency by 10%, that would basically reduce the global greenhouse gas emissions by 1%, right? So this is a notable number, right? And obviously a 10% improvement is significant, but it's not a 50% improvement, right? It's not an 100% improvement. Like this is feasible, right? Like improving energy efficiency by 10% is feasible, and this will actually, if we can do this across industries together with everybody that works in this field, then we can make a notable difference in this global greenhouse gas emissions, right? So that's really, I think, what drives us and what we have kind of front center on our target, saying, hey, look, this is what we're working towards, right? And we work with our customers actively to get that 10% improvement, so they can measure that and then bring that back up to the board and say, hey, look, this is what we've done, right, from a rotating equipment perspective. So that's very exciting to be able to be part of. Looking at AI, right? AI, very hot topic, and if you scroll through the agenda of this conference, a lot of the presentations have AI, machine learning in their titles, right? It's being applied in lubrication and in any field imaginable. AI today is being experimented with or being used at scale. But specifically when it comes to reducing greenhouse gas emissions in this type of industrial environment, today one of the big applications of it is process optimization, right? So one will use a time series based system and look at typically data historian data, right? So your OSI Pi or your SCADA system where the historical data lives, and basically apply AI models to that to try to optimize the process, right? So there was an example here of McKinsey, right, in the cement industry, where they say, okay, that kind of your first improvement, process optimization is mechanical, right? Just getting better equipment that can do the job more efficient, right? Next step is, okay, now using more advanced process control techniques, right? So more PLC, DCS controlled systems. That's kind of the next big improvement from a process optimization perspective. And then the next step is like, okay, those are the more traditional ones, right? And most companies have went through those optimizations already. Now the next step is, okay, now we start applying these AI asset optimizer models. That is kind of generic AI where they look at time series data and look at all the trends, and computers are very good at that, right? And finding, hey, these and these are the key influencers to my efficiency, and that's how they influence the data, how optimized my equipment runs. So that's how they then say, okay, that's kind of a first level of AI optimizing your process, right? Saying, okay, if I tweak these and these parameters, we can improve. And again, you see there's like a 6% jump in a 6.5% jump in potential process optimization. And that's really less energy basically being used for the same output, right? And then that goes a step further, right? Because a hardware upgrade is kind of a one-time thing, right? But these AI asset optimization or process optimizations, they can actually continue learning, right? And they will find, because obviously your process is not constant, right? Maybe your input materials are changing, maybe your output requirements are changing. So this AI model keeps learning and keeps looking over what the system is doing and keeps finding ways to improve, right? Because nothing is static anymore, right? Every process is dynamic today, and therefore it's a continuous improvement, and that basically brings us to 10% energy efficiency gains, right? By using these AI models, kind of this generic AI, as we call it, like the big data approach, right? Looking at a lot of parameters and finding the key influencers on the outputs and then optimizing those. Going one further, here we go. Now, what's another way that AI can help us reduce greenhouse gas emissions, and that's one that's less applied today, is basically going on an equipment level and identifying bad actors, right? So by out of our data for all the equipment, other thousands pieces of equipment that we're monitoring, we know that roughly 8% of them at any given time has an active fault, right? So the question is, do you know which one it is, right? And if you do you know what you need to do to resolve that, right? So that's another way where AI can help us by, first of all, identifying those 8% of equipment that need the attention, right? By doing some automated fault mode and severity identification, right? Kind of more the traditional predictive maintenance approach. And then in an ideal world, we want to, if we're trying to improve greenhouse gas emission, we want to measure that against energy efficiency, right? And that's really the step that predictive maintenance really never made, right? They say, hey, we can find issues and we're very good at that. But now how does that link to my energy efficiency is something that was never really looked at scale, at least. And so that's really how AI also can help us reduce greenhouse gas emission, right? By finding these bad actors and telling us where our efforts should go, where our investments should go. And so that, and then the big question is how does it influence our energy efficiency, right? Because that's the big question mark when we talk about greenhouse gas emissions and how to reduce them. So look very briefly at predictive maintenance. Excuse me. Looking very briefly at predictive maintenance. Today we have advanced wireless hardware, right? There's a number of vendors out there with very capable hardware to monitor these pieces of equipment. Can be wireless, can be wired, and there's a lot of good equipment out there to monitor equipment. We see more and more solutions now using some AI and ML models to try to do some anomaly detection and help the customer with kind of the first level of analysis. And then some systems take it a level further, right? They will actually try to identify the specific fault mode that is active, and then even rank it based on maybe remaining useful life, right? How long does this equipment have till it reaches the end of its life, so that you really know that a maintenance action is needed, right? So that's something that predictive maintenance has been focused on, right, since the 50s, basically trying to identify failures in an early stage and then warn the customer to assure that they have sufficient time to replace the equipment. And then if we're really end of life, like giving that last flag saying, hey, okay, now action is really required, right? So today at scale, unplanned downtime is being avoided. Maintenance costs are reduced based off that, right? And millions of dollars are being saved, right? And as I show here, right, it started in the 50s when vibration technology started to be used in this industrial setting, and today we've evolved quite a lot from there, right? So this is a trusted technology, but now the question is, how can we use the same technology to help us improve our net zero, right? Because that's really where predictive maintenance was really never meant to go, right? It was really meant to avoid unnecessary maintenance and unplanned downtime, right? So the question is, how do we take that a step further? And the big question there is or the link between the two is equipment efficiency, right? If our equipment, what is equipment efficiency? Basically, how much power do I need to provide here versus how much power do I get out of this equipment, right? And typical electrical motor, right, which drives maybe 75% of all the rotating equipment in the world, will have three main influences on efficiency. One is at the nominal load, right? If you're running far away from the nominal load for the motor, you will run at a less efficient rate, right? So that's something where your process optimizer works on, right? They try to find those ideal running conditions for equipment. Next one is a potential electric wear or problems that they will also reduce efficiency of the equipment. Or the next one is, and that's a big one, and that's where the link with predictive maintenance is mechanical faults, right? Because this will increase friction, and obviously friction is a pure loss, right? So now your whole machine train runs less efficient simply because you're having to use power to overcome a bearing fault or lack of lubrication or any of the above, right? And a good example there on the bottom, there was a study from Proof Technique, a company I used to work for, that basically calculated that as a misalignment of an equipment, right, a pump motor misalignment, your typical coupling misalignment, can increase power consumption by 10%, right? So something that is simple to detect and simple to correct can have a significant influence on power consumption, right? So that's something that kind of stuck with us and say, hey, how can we use that? And then the question is, how can we measure this energy efficiency, right? With your standard vibration and temperature sensor, obviously you cannot measure how the energy efficiency of a motor is in real time changing, but a nice thing is that some systems out there are starting to use magnetic flux as well. And the initial use for it was really to get an accurate speed for the equipment, right? Using the frequency of the magnetic flux together with the number of poles and the slip to define, hey, what is the running speed of an electric motor? And that's really how we've been using it for a couple of years now. But then one thing kind of came to mind saying, hey, this amplitude of the magnetic flux is really directly correlated to the power consumption of the motor, right? Because at the magnetic field in the motor is what you're measuring, and the stronger that magnetic field is, the more power is being generated, right? So by monitoring the amplitude of the magnetic flux, you're indirectly basically monitoring the power consumption, right? Because they're related to each other, right? You see that the power consumption is proportional with the square of magnetic flux, right? So that's really an interesting point, saying, hey, by measuring this magnetic flux and how it's changing over time, right? Because you're not measuring the absolute magnetic flux, but you're measuring how that energy efficiency is changing. That's how you can get a grasp of efficiency of the equipment. And going one further to the fault modes versus energy consumption is basically, if you look here, we have how does this work in practice, right? We have reliability and net zero, and basically by we monitor machine health, right? Like a lot of wireless or wired SCBM solution providers do. And then on top of that, by using that magnetic flux, we can start monitoring changes in the equipment efficiency, right? So now we can link those both together by saying, okay, in this example, you see the fan there, for example, hey, there is a severe fault active, and because we measured this equipment when it was in a good stage and during that fault developing, we measured that magnetic flux amplitude difference over time, we can now say, hey, for the same output and for the same process requirements, we're using 5 to 7% more energy, right? So that's that loss in energy efficiency. And by having some basic parameters of the equipment, that cost of energy and the horsepower of the equipment, you can actually calculate purely how that influences your CO2 output, right? So you have a direct measure of how this influences your greenhouse gas emissions, right? Excuse me. And that's really, really powerful, right? So instead of just using your equipment criticality and using maybe how severe a specific fault is to define your maintenance actions, there's now a third driver or a third parameter that maybe is going to become more and more dominant in the future is, hey, how is this influencing my greenhouse gas emissions, right? Because if my target is net zero, then if I can manage and measure the changes in my energy efficiency, this can then be directly correlated and say, hey, we took this maintenance action at this moment in time, and yes, because there was a fault active, or because we had a good maintenance, we need to take the action. But hey, this also decreased our energy efficiency, right? Or increased our energy efficiency by 5% for that piece of equipment, and you can directly calculate basically the ROI based on that. You can directly calculate the ROI based on that measurement, right? So that's really how linking the maintenance action to that energy saving, and then that same maintenance action can be directly linked to your CO2 emissions, right? Because it's a very straightforward calculation, and we can measure direct ROI, right? It's like, hey, we spent $7,000 to do an alignment on this piece of equipment. Oh yeah, and it reduced our energy efficiency, or increased our energy efficiency by 5%. So if we would have ran this for 6 months more at the same setup, it would have cost us X amount of dollars, right? So, and now it becomes directly measurable, not only from like a process perspective and an unplanned downtime perspective, but from a perspective on energy efficiency and how that contributes to our net zero targets, right? So that's kind of a different angle of looking at this topic, and that makes it really really exciting, right? Like that, coming from myself and a lot of people here coming from a very traditional reliability and condition monitoring background, and I've always wondered, like, hey, how can I contribute my piece to the net zero targets that I put for myself and that I put for my customers, or that my customers put. Well, this is how we can contribute, right? We can measure energy efficiency, and we can then link that back to an actual cost and CO2 reduction based on that maintenance actions that we take, right? So I think it's very exciting to be able to link, as a predictive maintenance engineer, to link your efforts back to, hey, how am I helping global greenhouse gas emissions to be reduced, right? So that's very exciting. Running out of the time here, and we're getting to the end of it as well, is that what do we talk about mainly, and what is today, what is net zero, right? I think it's one of the biggest long-term challenges that every company, or that we have as the population of this world, right? And that some simple calculations there, that if we can improve our energy efficiency by 10% of rotating equipment, we can reduce 1% of greenhouse gas emissions around the world, right? And 1% doesn't seem like a lot, but that makes a difference, right? So that's really what drives us to keep pushing this topic. And then we talked about how AI is used already today, right, for process optimization. That's a very good application for it. And then taking it one step further, right? If you use our existing predictive maintenance technology that's already powered by AI, and can help that to identify bad actors and define criticality of your maintenance actions, not based on uptime of the equipment, right, or unplanned downtime, or per se cost, but based on your environmental impact, right? So now one can improve in such way. By doing that, by measuring that energy efficiency degradation, right, based on equipment that is wearing out or equipment that has a fault active, we can actually directly measure our ROI of our maintenance actions as well, right, or of replacing equipment, for example, right? So that's a great way to save capital and to help save the environment, right, by having a measurable impact. Okay, we got 5 minutes left here. I'm not sure if we had many questions on the book here, but if not, I want to thank everybody for joining me here today, and thank you to Sanya and the team of LRVS to putting this conference together, and happy to be able to present here my part of it.
Thank you, Dries. Do we have any questions? Looks like they're going to let you off easy, man.
Seems like it, yeah. Anyhow, so again, thank you, everybody. Thank you for hosting this, and look forward to some of the other presentations here in this packed agenda with some great content. So thank you, everybody.
Have a great day. Thank you, Dries.